Okay, so today we're going to go from the outside of the atom to the inside of the atom, particularly the nucleus of the atom, rather from the outer part of the atom to the inner part, the nucleus of the atom. And so we're going to talk in particular about nuclear physics and radioactivity. So the nucleus consists of two basic particles, protons and neutrons. Protons have a charge of +1, neutrons are neutral. They have a very, very similar mass. If you look to three significant figures, they're both 1.67 times 10 to the negative 27 kilograms, but the neutron is slightly more massive. Not by a whole lot, but enough to be noticeable. So all atoms of a given element contain the same number of protons. So when we talk about an element and its place in the periodic table, we're talking about the number of protons in the element. Um, there can be different number of neutrons in the nucleus for a given element. And so different forms are, different nuclei with the same number of protons but different number of neutrons are called isotopes. And so you can have multiple isotopes of a different, or of a given element. Again, the protons remain the same, but the neutrons are different. So we let A, the mass number, be the number of nucleons, protons, and neutrons in a nucleus. So A is equal to Z plus N. An isotope is denoted in the following form. So it's typically written like this. So in the top left, you have the mass number, again, protons plus neutrons. X is the chemical symbol. And then Z is the simply the number of protons, or the atomic number. Sometimes the Z is optional because the chemical symbol will imply what the value of Z is. But usually you will see it written with the number of protons plus neutrons, in the top left corner. The size of a nucleus is approximately given by this formula where you have 1.2 times 10 to the negative 15 meters. That's the size of a hydrogen nucleus, one proton, and multiplied by the mass number to the 1/3 power. So, a helium nucleus will be slightly bigger than that, and you work your way forward. So, a deuterium nucleus will be slightly bigger than that. A tritium nucleus will be slightly bigger than that. A helium nucleus, the typical helium nucleus, has a value of 4 for A, and so you can see how it goes up from there. A lot of times in atomic and nuclear physics, the mass is expressed in terms of what are called unified atomic mass units. They are normalized so that a carbon 12 atom has a very precise value of 12.000 for as many decimals as you would like units. So 1 unit to 5 significant figures is 1.6605 times 10 to the negative 27 kilograms. And so one mass unit it's also equivalent to 931.51 mega electron volts per C squared. So basically, or over C squared. So you take the 931.51 mega electron volts, you convert that to joules, you divide it by C squared, you get the 1.6605 times 10 to the negative 27 kilograms. And then with the mass of the proton, it's 1.007276 mass units, or 938.27 mega electron volts over C squared. The neutron is 1.008665 mass units, or 939.57 mega electron volts per c squared. Again, there's a slight difference in the mass of the neutron compared to the mass of the proton. But these are a couple of conversion factors that are worth knowing depending on uh, what you need, or what quantities you're looking at evaluating. So if you're talking about mass, you're probably working with mass units or with kilograms. But if you're talking with energy, about energy exchanges, it's usually more convenient to work with the mega electron volt over c squared units. So question number one, a pi meson has a mass of 139 mega electron volts over c squared. What is this in atomic mass units? So let's set up our whiteboard. And so uh, the mass is equal to 139 mega electron volts per c squared. So we need to figure out how many atomic mass units in 1 megavolt per c squared. So in the previous slide, one mass unit is equal to 931.51 mega electron volts per c squared. So you put 1u divided by 939.51 mega electron volts per c squared. Let's double check that I got that number right. 931.51, excuse me. And so that's the conversion. So you're dividing the 139 by 931.51. And you get 0.149 mass units. So it's about 15% the mass of a proton or a neutron, basically. So let's go to another example. What is the approximate radius of an alpha particle, helium-4? So 2 protons, 2 neutrons. So going back to the equation, or the approximate equation for the size of the nucleus, R is equal to 1.2 times 10 to the negative 15 meters times 4 to the 1/3 power. So 4 to the 1/3 power is about 1.6. And so you get 1.9 times 10 to the negative 15 meters. And so so a hydrogen nucleus, or at least hydrogen with only the proton, is 1.2 times 10 to the negative 15 meters. Typical helium nucleus with 2 protons and 2 neutrons, 1.9 times 10 to the negative 15 meters. So the atomic nucleus, much like the electron, has a spin. It has some angular momentum. It doesn't sit in place. It does rotate. So it has rotational kinetic energy, and it has angular momentum. And so a nucleus has a nuclear spin quantum number I, or capital I, that can be an integer or a half integer. And so the total nuclear angular momentum is equal to the square root of I times I plus 1 times h bar. So again, you get that relationship between a quantum number and the angular momentum. That keeps popping up a lot. And so we're going to define what's called a nuclear magneton. And so that's equal to E times H bar times, or divided by 2 times the mass of the proton. So that's a constant that you can figure out. The magneton of a proton is 2.7928 times this number. The magneton of a neutron is negative 1.9135 times the nuclear magneton. So neutrons and protons tend to spin in different directions. So that brings us to nuclear binding energy. So the total mass of a stable nucleus is always less than the sum of the masses of its separate protons and neutrons. And so that difference is called the binding energy. So you need to supply that much energy if you want to break the nucleus apart into its constituent protons and neutrons. And but that relationship is also the basis of nuclear fission and nuclear fusion. And so the strong nuclear force is the attractive force that keeps protons packed together within the nucleus. Remember that the protons are positively charged. If the only force acting on the protons were the electrical force, they would repel each other. You couldn't have a stable atomic nucleus with only the electric force acting. There has to be an additional force, that attracts the neutrons, and that, inside the nucleus is stronger than the electrical force, or at least can cancel out the electrical force, so that the neutrons are held in, or rather the protons are held in place, and the neutrons as well. So now we're asked to use Appendix X to calculate the binding energy of deuterium. So let me quickly get the textbook out. Appendix F is located in the back of the book on page A14. And so the binding energy, again, is just the difference between the rest energy, or the energy of the individual parts minus the energy of the whole. So let's go back to the whiteboard. So the binding energy is equal to, and this is for deuterium. So the energy of a proton minus, or plus the energy of a neutron minus the energy of deuterium. So the energy of the proton is, and we can go back to the, go back a couple of slides. We'll write that as in mega electron volts. So that's 938.27. And that's mega electron volts, so 1,000,000 electron volts, plus the energy of the neutron, which is 939.57. And you're subtracting from that the energy of deuterium. So deuterium in atomic mass units is 2.014102. And you're multiplying that by the atomic mass unit. And so that's 931.51. So what do you wind up getting? So it's 938.27 plus 939.57 minus 2.01402 times 931.51. And so what you get is 1.76 mega electron volts. So that's the binding energy of deuterium. Again, you take the rest energy of the individual parts and then subtract from that the rest energy of the whole. And that gives you the binding energy. And that brings us to radioactivity. So radioactivity is when atoms emit radiation or particles without any prior stimulation due to the disintegration or decay of an unstable nucleus. So for whatever reason, and you can think of this, from a quantum mechanical perspective, as kind of like barrier penetration. That's with radioactive isotopes, the barrier is easier for portions of the nucleus, parts of the nucleus to cross, and so that's typically what happens, at least with alpha decay. With beta decay, an electron is emitted. And with gamma decay, a high energy photon is emitted. So there are basically three ways that uh, that you have radioactive material. One, you're emitting a helium nucleus, two protons and two neutrons. So that's when something gets ejected from the nucleus. With beta decay, an electron is kicked out. So an electron somehow gets enough energy to be booted from the atom or to break free from the atom. With gamma decay, that's also a nuclear process. You're talking about a high energy photon being emitted, typically quite a bit higher energy than you're likely to see from interactions involving electrons. But the nucleon number, regardless of the radioactive process, the nucleon number is conserved. So you have the same number of protons and neutrons. It's possible, certainly with beta decay, it's possible that uh, you can have a neutron become a proton and kick an electron out, or become a proton and an electron, and so you're preserving charge. Um, but again, the electron is kicked free from the atom. The atom typically doesn't become ionized at that point, but the atomic number changes, but the mass number does not. So let's start with alpha decay. Uranium decays into thorium and helium. And so that's an alpha particle. Radium decays into radon and helium. So, these are typical radioactive isotopes. And, they emit a helium atom. And so their atomic number changes and the mass number, the mass number of the remaining element changes, but the total mass number is conserved. And the electric charge is also conserved when this happens. So when the daughter nucleus is different from the parent nucleus, that's called transmutation. So basically, in alpha decay, one element changes to another element, and so the daughter nucleus is different. And so you start with the original element labeled N. That's the parent nucleus, and then you have the daughter element or the daughter nucleus. A has been reduced by 4, Z has been reduced by 2, and you have a helium atom that gets ejected, or at least a helium nucleus. Sometimes it may take due to electrical attraction, may take some electrons with them, but that's not a given. The mass of an alpha particle is 4.002603 mass units. So again, you don't expect the mass unit to differ, or the mass of a particle in mass units to differ significantly from its mass number, certainly for relatively small, relatively low mass numbers. So the mass of the parent nucleus is greater than the mass of the daughter nucleus plus the mass of the alpha particle. And so the lost mass becomes the kinetic energy of the alpha particle plus the daughter nucleus. You can figure out the relative kinetic energy of each part. Momentum is going to be conserved. So if you assume the particle was at rest initially, or you define a reference frame where the parent particle or the parent nucleus was at rest, then the momentum vectors of the daughter nucleus and the alpha particle are going to be equal and opposite. But remember, again, because the total momentum is going to be zero. And from that, you can figure out the relative kinetic energies of each. But you still have an additional Q value. That's the, that's the kinetic energy. And so that kinetic energy comes from the fact that the daughter nucleus and the alpha particle have less rest energy than the parent nucleus did. And so as a result, that energy gets converted to kinetic energy. In alpha decay, there's not an additional emission of an electron, for example, or a gamma ray, but we'll talk about those in a couple of minutes. So let's do an example. A nucleus of mass 256 U, initially at rest, emits an alpha particle with a kinetic energy of 5.0 mega electron volts. What is the kinetic energy of the recoiling daughter nucleus? Okay, so the kinetic energy, and there are a couple of ways to think about this, but the easiest way is to assume 256 U and that the alpha particle is 4. And so the alpha particle has a kinetic energy of 5.0 mega electron volts. So we're going to assume that the daughter nucleus has a mass of 252 atomic mass units. So we'll assume the mass of the daughter nucleus is 252 U, and the mass of the alpha particle is approximately 4 units. And so the kinetic energy is equal to P squared over 2m. So the first thing you want to do is check to make sure that whether we're talking about relativistic or non-relativistic kinetic energy. So let's figure out the velocity of the alpha particle, at least in the classical sense. And so that's the square root of 2k over m. So that's the square root, and so that's 5.0 mega electron volts divided by, and that's 1.6 times 10 to the 13 because it's mega electron volts rather joules per mega electron volt as opposed to joules per electron volt. So it's 10 to the 13 and divided by m. So the helium nucleus has 4.002603. And that's its mass units, and you're multiplying that by 1.6605 times 10 to the negative 27 kilograms. So this gives you the mass units. So that's 2 times 5 times 1.6 times 10 to the 13 divided by here, hold on. This is you're dividing by this. So that's 2.5 times or divided by 1.6 times 10 to the negative 13 mega electron volts per joule. All right. So that converts it to joules. So that's 2 times 5 times, or rather, divided by 1.6. Hold on. It's 1.6 times 10 to the negative 13 joules per mega electron volts. This is what I get for trying to go through the lecture quickly. So 2 times 1.5 times 1.6 times 10 to the negative 13 divided by 4.002603 divided by 1.6605 times 10 to the 27. And then you're taking the square root of that. And so that's 8.5 times 10 to the 6th meters per second. So that's subrelativistic. So you can use this version, relating kinetic energy to momentum. And so we know the momentum is going to be the same for both. So the p squared is equal to the square root of 2mk. And so that's equal to 2 times the mass and actually we know that the magnitudes of the momentum are the same for both objects. So m, the mass of the daughter nucleus times the velocity of the daughter nucleus is equal to the mass of the alpha particle times the velocity of the alpha particle. And we know that it's subrelativistic, so we can keep it like that. And so and we are asked for the kinetic energy of the recoiling daughter nucleus. Yeah, so we don't need the velocity either. We just need kinetic energy. So K is equal to P squared over 2M. And so this is the kinetic energy of the daughter nucleus. So it's P times the daughter nucleus squared's momentum divided by 2md. But this is just the momentum of the alpha particle. So we can write that as the mass of the alpha particle squared times the velocity of the alpha particle squared divided by 2 times the mass of the daughter nucleus, which is uh, 2 times the mass of the daughter nucleus. So we can plug all these in. So we have 4.002603 again times the 1.6605 times 10 to the negative 27. And you're squaring that, squaring both these terms. And then 8.5 times 10 to the 6th meters per second, and you're squaring that. And you're dividing by 2 times the mass of the daughter nucleus, which is 252. And again, that 1.6605 times 10 to the negative 27 kilograms. So we can drop one of these out and then go with that. And okay, so that's the numerator. And you get 3.8 times 10 to the negative 15 joules. In mega electron volts, you divide that by 1.6 times 10 to the negative 13. And so that's 0.024 mega electron volts. So that's the kinetic energy of the daughter nucleus. So it's a relatively small fraction of the kinetic energy of the recoiling daughter nucleus. And again, you can figure that out because momentum has to be conserved. So with alpha decay, the alpha particle is subject to a square well potential due to a strong nuclear force inside the nucleus and a Coulomb potential immediately outside the nucleus. So how does that look? You can think of it like this. You have your so we'll say x equals 0 and x equals L. And so, and we'll make this a different color. So you have the potential energy in blue looking something like this, and then decaying on the other side of the nucleus. So it kind of looks something like that. And so you have this barrier that's, in classical mechanics, the particles within the nucleus wouldn't be able to penetrate that barrier. But in quantum mechanics, it's allowed. And so, every so often, a piece of the nucleus crosses through that barrier and so gets to the other side. So I mean, you think the particle in the box, so it's held firm in place, but every so often you have enough energy inside that you can get out, and so it looks something like that. And so quantum mechanics allows for the alpha particle to get enough energy to tunnel through the potential barrier. So every so often, an alpha particle breaks free from the nucleus because of barrier penetration. Now let's talk about beta decay. And so for here, a neutron is transformed into a proton plus an electron. So sometimes neutrons can decay. And when they do, again, charge is still conserved. You have a proton and electron, but usually the electron gets booted out of the nucleus as a result, or it gets enough kinetic energy from the decay that it escapes the nucleus very easily, whereas the proton typically remains in place. Energy and momentum conservation required the presence of an additional particle in the process. So when people were studying beta decay, there was some additional energy and momentum not accounted for. So they postulated that another particle had to be involved that doesn't interact with things very easily. And it turned out that that was true. And so that particle is called the neutrino. So it's a neutral charge. It has a very small amount of mass. The maximum bound of the mass is 2.5 times 10 to the negative 37 kilograms. Initially, it was thought like a photon to be massless, but now scientists are confident that a neutrino has at least some mass. And it has a spin of 1/2 h bar. Positrons can be emitted if the beta decay occurs in an isotope with relatively few neutrons per proton. So below the stable end of things. And so you look, this line is where the number of protons equals the number of neutrons. So a line with a slope of 1. And for an atomic number up to about 20, you typically have as many neutrons as protons for a stable nucleus. But if the, as Z increases, the ratio of neutrons to protons in a stable nucleus increases above 1 as well. And so for positrons to be emitted, to get a positron and an antiproton, typically what you need a nucleus that's below or that has fewer neutrons than the stable nucleus. Most of the time, most radioactive isotopes are higher, more neutrons than the stable nucleus. So that's something to keep in mind. So what's the maximum kinetic energy of an electron emitted in the beta decay of a free neutron? So what's the maximum kinetic energy? So that's assuming nothing goes to the neutrino. So again, you have a neutron going into a proton and an electron. So let's set this up on the whiteboard. So you have the energy of the neutron. Let's get back to black for this. The energy of the neutron is equal to the energy of the proton plus the energy of the electron plus Q, whatever additional energy is involved. Now, this could go into the kinetic energy of these particles, and typically because the electron is a lot less massive than the proton, it will have a much greater kinetic energy, as a result. So if it has, about 1/2000th the mass, it'll wind up having about 2,000 times as much kinetic energy. And so given that, so you want as much of the, so basically the problem is asking what's the maximum kinetic energy of an electron. So we're assuming there's no neutrino, or the neutrino is taking a negligible amount of kinetic energy. So in that case, we'll say Q is entirely the kinetic energy of the electron. So this is the maximum possible energy or kinetic energy the electron can get from the decay. So it's the energy of the neutron minus the energy of the proton minus the energy of the electron. So these are the rest energies. And so going back to the beginning, the mass of the neutron is 939.57. And that's mega electron volts. The rest mass of the proton is 938.27. And the rest mass of an electron, and you can look that up, that I believe is in the front cover. And I believe it's actually something less than 1. But let's get that specifically. 0.5511 mega electron volts. So we're right, minus 0.51 mega electron volts. And so if basically all this goes to the kinetic energy of the electron, you get you get 0.79 mega electron volts. So that's the remaining energy. And so basically when they ask what's the maximum that can go to the electron, that's assuming there's no neutrino, or that the neutrino is getting a negligible amount of kinetic energy. So 0.79 mega electron volts. So then we go to gamma decay. And so like an electron, a nucleus itself can be in an excited state, whether it was, some sort of collision gave it extra energy, or perhaps it absorbed some sort of photon. The possible energy levels are much farther apart than those of an electron. So the photons that get emitted are much more energetic than those of an electron. And so that's why you have the gamma rays. Excited states are caused by collisions, or perhaps by a previous radioactive decay that gave the electron some energy, or rather gave the nucleus some energy. But the general form, so this is an excited nucleus. That's what the asterisk means. And so it goes down to a state, I guess sort of the ground state, or a less excited nucleus, plus the gamma ray. And so the lithium-7, so lithium is the atomic number 3. The lithium-7 nucleus has an excited state 0.48 mega electron volts above the ground state. What wavelength gamma photon is emitted when the nucleus decays from the excited state to the ground state? So we know its energy, and E is equal to hc divided by lambda. So we expect the wavelength to be very small. Remember, the smaller the wavelength, the higher the energy. So E is equal to hc over lambda. And so lambda is equal to hc over E. And so H is 6.626 times 10 to the negative 34 joule seconds. C is the speed of light, 3.00 times 10 to the 8 meters per second. And we are given an energy of 0.48 mega electron volts. And the conversion again is 1.6 times 10 to the negative 13, not negative 19 joules per mega electron volt. And I apologize for the confusion earlier. And so this gives the wavelength. And again, we expect it to be a low wavelength photon, but how low? 6.626. and you get 2.6 times 10 to the negative 13 um, meters. So even then, that's about 2.6 ten thousandths of a nanometer. So we're talking a very small wavelength. So that brings us to the rate of decay. How quickly do things decay? So for a given sample, the number of decays dn over a time dt is proportional to both dt and n, the present number of radioactive nuclei. So, the more radioactive nuclei you have, the more then will decay over a time dt. And similarly, the longer the time dt, the more you can expect them to decay. And so you have dn, the differential number of decays, is equal to negative lambda n dt, or you can simply write that as dn over dt is equal to negative lambda n, where lambda is a proportionality constant called the decay constant, and it's substance specific, like so many other things we've talked about in physics. And so the term for the derivative of n with respect to dt, or at least the absolute value of it, that's equal to lambda n, and it's called the activity. So the decay constant depends on the substance. The activity depends on not only the substance, but on how much of it that you have, and or at least how much of the radioactive substance that you have in a sample. And so you have the radioactive decay law. You just integrate. And so you have the total number of radioactive nuclei is equal to the n naught, which is the number of radioactive nuclei you have at t equals 0, and then times e to the negative alpha t. And so that's the basic equation. So that the rate of decay for any radioactive substance is exponentially decreasing. So over a certain amount of time, half of the radioactive substance will decay. Over that same amount of time, half of the remaining substance will decay. And over the same amount of time, half the remaining substance will decay. And that's why it's convenient to talk about the decay rate in terms of the half-life. And so, the half-life and the decay rate are very closely related to each other. If you know one, you can figure out the other. So the half-life is equal to the natural log of 2 divided by lambda, the decay rate. And similarly, the decay rate is equal to the natural log of 2 divided by the half-life. And so the mean life is the average lifetime of a radioactive sample. And so that's equal to 1 divided by lambda. And it's also equal to the half-life divided by the natural log of 2. So that's the average lifetime of the radioactive nuclei in the sample, or what the average lifetime of a given nuclei, the average lifetime of all the nuclei together is going to be in that sample. So oftentimes you have what's called a decay chain, where a radioactive isotope will decay into another radioactive isotope, which will then decay into another radioactive isotope, and so on and so on, and until you get to a stable nucleus. So what happens is that unstable isotopes with relatively short lifetimes have their supplies readily replenished. So if you're in an intermediate state, whenever the material decays, something of a higher mass number will decay to that. So radon 226 is an example. So the radon will decay, but a higher radioactive isotope or a higher mass number radioactive isotope will decay to radon 226. So how does this look? And so there's an example on page 1121 in the book of a decay chain. And there are often multiple combinations in the decay chain. And so you're starting here with uranium-238. And so the red line corresponds to alpha decay. The blue line, or rather the green lines, correspond to beta decay. So in a beta decay, the mass number is constant, but the atomic number actually increases by 1. So you have uranium decaying to thorium-234 here. But then 2 alpha decays get you back to uranium, and that's uranium-234 now instead of 238. Then you have a series of alpha decays. And like I said, there are some materials that can either alpha decay or beta decay. So a combination of things happen. But eventually you wind up getting to the bottom, which is lead-82. So uranium will eventually decay into lead, and you can see that some of the half-lives are very, very long time. So the decay rate of uranium-238 is 4.9 times 10 to the 9 years, 4.5 billion years. So, and then the decay rates for the alpha decay for uranium-234, that's 2.5 times 10 to the 5. So that's only 250,000 years, which may seem like a long time, but not compared to the decay rate of uranium-238. So these steps can take a very long time, but eventually you'll get some lead out of the sample. And radioactivity makes it possible to determine the age of certain things. So we'll start with carbon dating. So carbon-14 is a radioactive isotope of carbon. Living things exchange carbon with the atmosphere and maintain the same ratio of carbon-12 to carbon-14 as the air. So whatever carbon-14 we're breathing out, we're breathing some in, and we wind up maintaining the balance. And so whether we're breathing in or out, whether, when we exhale carbon dioxide, whatever carbon we're consuming from food, ultimately we're maintaining a balance with the air. But when organisms die, they stop interacting with the air. And so whatever carbon-14 is in the organism at the moment of its death doesn't get replenished. And so the C14 gradually decays. And so you can use the ratio of C12 to C14 to determine the age of the organism, because we know what that ratio is in the air and in a living organism. And so, the ratio of C12 to C14 is going to be higher in a dead organism, but we can use that to determine the age of the organism. And we can do it fairly reliably between 1,000 and 60,000 years old. It's extremely useful for dating human sites with organic material in it. And so that makes it a very useful dating tool for certain things. And certainly for tracking human migration, for example, in the past, going up to 60,000 years old, you can use carbon-14 to date it fairly accurately. And then we have the radioactive decay of uranium. Uranium has a half-life of 4.5 times 10 to the 9 years, so 4.5 billion years. Not a whole lot less than the age of the Earth, which I think is 5 billion years. And it's approximately 5 billion years. So that means it's a very useful half-life for dating rocks and for dating a sample that has, a rock bed that has fossils in particular. So you can figure out at what time in the Earth's history, if the rock contains some uranium, uh, you can figure out what time in the Earth's history um, that rock was formed from the ratio of the uranium to the amount of lead that it has. So you can look at the different steps that are involved from that. So what is the decay constant? We're going to an example. What is the decay constant of uranium-238, whose half-life is 4.5 times 10 to the 9 years? So just setting this up, the decay constant is equal to the natural log of 2 divided by the half-life. And so we can leave this in inverse years. We don't have to put that into inverse seconds if we don't want. And so you take the natural log of 2, and which is 0.693. And you divide that by 4.5 times 10 to the negative 9. Or rather, excuse me, 4.5 times 10 to the positive 9. You'll get a negative number as a result. And so that's 1.5 times 10 to the negative 10 inverse years. And so you don't have to convert it to inverse seconds if you don't want to. And oftentimes, if you're dealing with years, it might be beneficial not to. And then B, the decay constant of a given nucleus is 3.2 times 10 to the 5 inverse seconds. So what is its half-life? So here, you're given lambda and asked to solve for the half-life. So it's the natural log of 2 divided by lambda, and we'll leave this in seconds. So that's 3.2 times 10 to the negative 5 inverse seconds. And so you get 21,660, or 2.2 times 10 to the 4 seconds. So I will pause here. So 2.2 times 10 to the 4 seconds. And so let's remember, a day has about 86,000 seconds in it. So it's about a quarter of a day, about 6 hours, if you were to do the math. Okay, so let's press on. A radioactive material produces 1,280 decays per minute at one time, and 3.6 hours later produces 320 decays per minute. And so what is its half-life? Well, okay, so we have, setting up the whiteboard, we'll clear all this. So we have lambda n1, the activity. And so that's how many decays per minute. And so lambda n1, well, actually, we'll call it lambda n naught. So we'll say the initial one is at t equals 0. And so lambda n naught is 1,280. And then lambda n at a later time t is, which we're given, is 320. And that's t is equal to 3.6 hours. And so we're asked, what is its half-life? Well, we can figure out lambda. So going back to the equation, we have n is equal to n naught e to the negative lambda t. And we know what t is. So we can write n over n naught is equal to e to the negative lambda t. And then taking the natural log of both sides, we have the natural log of 1, or rather, well, we won't put that in yet. N over n naught is equal to negative lambda t. So we can write lambda as being equal to negative 1 over t times the natural log of n over n naught. So we can write that as negative 1 over 3.6 hours times the natural log of 320 to 1280, which is going to be the natural log of 1 over 4. So let's figure that out. And the natural log of a number less than 1 is going to be negative. So it's negative 1.38, and you're dividing that by negative 3.6, and you get 0.39 inverse hours. And so the half-life, which is what we're asked for, is the natural log of 2 divided by lambda. And so you invert that answer and multiply it by the natural log of 2, and you get a half-life of 1.8 hours. So that's doing this mathematically, and you can probably just figure out from looking at it, well, it went down by a quarter in 3.6 hours. So, but I went through the steps because, again, sometimes the math won't be that simple. So you were given numbers that you could probably figure it out, intuitively without going through the math, but it's worth it to go see the math in play. Now, what fraction of a sample of germanium-68, whose half-life is about 9 months, will remain after 2.0 years? Well, 2.0 years is 24 months. So that's something to keep in mind. And so the first thing we're going to do, we have the half-life. We'll figure out lambda. So let's clear this. So lambda is equal to the natural log of 2 divided by the half-life, which we are given. And so you can see it's going to be a bit more than 1/8. This should be the final fraction, because after 9 months, there's going to be half. After 18 months, there's going to be a quarter. So we have about 24 months. So it's going to be a bit more than 1/8, which would be 27 months, but it's going to be less than a quarter. So we'll see how this looks. So that's the log of 2 divided by, and we'll leave it in, we'll write this as 24 months. or rather the half-life is 9 months, excuse me. But we'll leave it in inverse months. 2 log divided by 9 is 0.077 inverse months. And then we have n over n naught, the fraction, is going to be equal to e to the negative lambda t. So that's e to the negative 0.077 inverse months times 24 months. And solving for that gives 0.16. So again, it's a bit more than an eighth, but not quite not quite a quarter. So it's right in the area that where we would have expected it to be. So then what is the activity of a sample of carbon-14 that contains 8.1 times 10 to the 20 nuclei? So carbon-14 is a half-life of 5,730 years. So the first thing we're going to need to do is figure out lambda. So lambda is equal to, and again, you can leave this in inverse years if you want. So that's 1.210 times 10 to the negative 4 inverse years. And so we're asked, what is the activity of a sample that contains 8.1 times 10 to the negative 20 nuclei? So R is equal to lambda n, which is 1.210 times 10 to the negative 4 inverse years multiplied by 8.1 times 10 to the 20. And so that's 9.8 to two significant figures, 9.8 times 10 to the 16 inverse year. And, if you want, it's definitely a number that you can reduce from years to seconds. And so the number of seconds in a year is 3.15 3.15 times 10 to the or 3.16 times 10 to the 7 seconds. So if you want, you can write that, you divide this number by 3.16 times 10 to the 7. You get 3.1 times 10 to the 9 per second. So you're getting 3 billion hits, 3 billion decays a second. From that. Again, you're dividing this total by the number of seconds in a year. So it's 3.1 billion decays per second. So that's still, a pretty large number of decays, even though it's, even for such a long half-life. And so it's not hard to spot, to find the activity. So how do you detect radiation? There are a few ways you can do it. The most basic way to detect the presence of radiation is a Geiger counter. It can detect charged particles that are passing through it. And it was a very useful way, certainly in the early days of nuclear physics. This was a very useful way of picking out radiation. You can also use what's called a scintillation counter, where the scintillator enters an excited state when struck by a particle and then emits visible light when it returns to the ground state. So if your scintillator starts to glow, you're in the presence of radioactivity. And another way is the photomultiplier tube. Converts incident light, or incident radiation is probably the better way of putting it, into an electric signal. And so, if the voltmeter is, connected to the photomultiplier tube is going up, that's telling you something, that you're in the presence of radiation. There are more high-tech ways of doing it if you want to get more precise. So you have silicon wafer semiconductors. A particle, they're fragile enough that a passing particle will etch a track onto the surface. So you can not only infer that a particle was there, but you can say something about its path. And so it's useful in particle physics, for example, because once you have the path, you can say something about its momentum, at least its direction, for example. And and also how far it traveled before it decayed further. So you can get some information. With photographic emulsion, ionized atoms leave a mark when the emulsion is developed. So if they pass through, you can detect that. And again, you can detect the track. And so the same with cloud chambers. Gas molecules condense on ionized particles as they're going through it. Again, that's another way of figuring out the track of a particle. And in a bubble chamber, the ions make bubbles in superheated liquid. So they go through, the superheated liquid. Wherever they make contact, you get gas, or the liquid evaporates, and you have these gas bubbles. And you can figure something out about the uh, energy the particle had, about the track that the particle had, and so you can figure things out from that. Another more high-tech way is a wire drift chamber. So the ions are attracted to high voltage wires, so the wires will pull the ions in, and then a computer analysis, a computer program will determine the track from how they interacted with a given high voltage wire and where. And so you can analyze things that way. And so there are a lot of different ways that you can detect radiation. Um, some relatively crude ways, but then some ways that can give you more information, like where it was, what direction it was going, how quickly it was going, so you can figure out magnitude and direction of velocity and momentum, for example. And these are things that make it possible to do particle physics, to do the kind of things we're going to be talking about in the last 2 or 3 chapters of the book and of the course. Okay, so that's all we need to do for today. So if you have any questions, you can email me before Friday. Otherwise, we'll talk then.